I've sort of skipped over the first part of this because we've done some of it. B, you've read about some of it already. And C, I don't know. We just need to move on a little bit because by the end of this week, I want to be finished section 2.2. And I don't know if you've looked at the cover, but section 2.2 is big. Okay? It's like got 2.2a all the way through 2.2l. All right? And we want to finish it by the end of this week. So we're going to go fast. Okay? So, first of all, I misspelled macroscopic. Can you guys see my mistake? I left off the S. Okay? Laura, could you close the door for us, please? Thank you so much. So you should know that a macroscopic property is an observable characteristic. So you need to know this. You should also know examples of macroscopic properties. So you want to know these. Okay, we are on page 1818. So what are some macroscopic properties? Concentration is a macroscopic property. Pressure is a macroscopic property. Color, temperature, density, pH, those are all macroscopic properties. And why do we care about macroscopic properties in the equilibrium unit? Because macroscopic properties remain constant at equilibrium. Okay. So now we're going to skip over where it says number 4, and we're just going to go to dynamic equilibrium. But before you read there, what I would like you to do is define dynamic equilibrium to your neighbor. So talk to your neighbor about what is a dynamic equilibrium, or you can just talk to yourself about what a dynamic equilibrium is. Okay, so a dynamic equilibrium, there are several different ways to define it. Here are 2 of them, because you always have to have both the dynamic part and the equilibrium part. So in our first definition, the macroscopic properties are constant, and that part tells us that we are at equilibrium. But changes continue to occur at the microscopic or particle level. I prefer particle myself because it is more accurate, because if things are microscopic, you can't really see you can't see particles under the microscope, okay? But most books will accept microscopic changes. That's what I've seen written in many textbooks, so I will also accept it if you write microscopic changes. Now this part, because it has to do with changes, this is the part which is dynamic. Because what does dynamic mean? Changing. Now in our next definition, which part is the equilibrium part? Yep. We have a reversible system in which the forward and reverse reactions continue to occur. Whoops. Hang on. A reversible system. What is wrong with me? I'm sorry. I'm making a mess. And I'm confusing myself and probably you. It's a reversible system, and the rates are constant and equal. That part is the equilibrium. But the fact that the forward and reverse reactions continue to occur, that part is the dynamic part. Okay? Not that it really matters that you be able to pick out the equilibrium part and the dynamic part. Just be aware that if you write a definition, it should include both the equilibrium part and the dynamic part. All right, we should be aware of the following things before we continue on. Changing the temperature will change the rates. Yes? But what do you remember? A change in temperature affects which rate more? Which type of reaction? The endothermic, okay? Do you remember what we call it? A change that we make to a system? Yes. And it's not just any old change we make to a system, it's a change we make to a system that causes the rates to be unequal. And that is called a stress. So for example, changing the temperature is a stress because it increases the rate of the endothermic reaction more than it increases the rate of the exothermic reaction. Now, once those two reactions are unequal, they will then proceed to the reaction will proceed to shift until the two rates are equal again. And so in order for a system to be at equilibrium, the temperature must remain constant, because if we're changing it, we're changing the rates relative to one another. And remember, in order to be at equilibrium, we must also have a closed system. Okay, I'm hoping that part is becoming familiar to you now. And finally, equilibrium can be approached from the left. I just want to introduce this language to you because you will hear this. Equilibrium can be approached from the left. What that means is if you start only with reactants, you can reach equilibrium. But if you start only with products, you can also reach equilibrium. So when we say an equilibrium can be reached either from the left or from the right, what we mean is if we start with reactants, we can reach an equilibrium. If we start with only products, we can reach an equilibrium. Okay? So starting with only products can also reach equilibrium. Okay, we're going to skip over this little paragraph at the bottom. I'll let you read it on your own time. And we're going to go to this page because there's some lovely little fill-in-the-blank stuff. I would like you to think, can you guess what would happen if we start with pure NO2? So what that means is at the beginning of the reaction, at the start, we have lots of NO2, and we don't have any N2O4. So what I would like you to do is I would like you with your partner to read through this little paragraph and see if you can fill in the blanks as you go. Okay? Give it a try.
Oh, I should have called. I went a little bit more. So it's now.
Hi. Oh, it's totally arbitrary. Totally arbitrary.
So it's just
Yeah.
you decide.
I decide. Yeah.
Okay, got it.
Yeah. We just had a question. How do we know that the NO2 is the product of the reaction? Totally arbitrary. It just depends on how I've written the reaction. I could have written it the other way, in which case the NO2 would be the reactant rather than the product. So it's totally arbitrary. Okay, so how would the reverse rate start out? It would start out fast. And the forward rate would start out at 0 because we don't have anything. That's supposed to be just a line. Sorry about that. 0. As the reaction proceeds in the forward, as the reaction proceeds, the forward rate would increase. It has to increase. It starts at 0. And we are making reactant because the reverse reaction is occurring. The reverse rate would decrease because we are using up product to make reactant. Eventually, the two rates would become equal, and an equilibrium will be reached. You could say dynamic equilibrium. I heard someone say that. And that was good. Okay, so regardless of whether we start with reactants or products, the forward and reverse reactions will proceed until an equilibrium is established. So reversible systems that are not at equilibrium will tend to move towards a position of equilibrium. So if you're not at equilibrium, you're going to move to equilibrium. It is the most stable state. Okay, equilibrium is the stable state. Okay, so here we have 6 characteristics or qualities of a system at dynamic equilibrium. Now, what I would like you to do is I would like you to notice that this is different from the 5 conditions necessary for equilibrium. How are they different? One is like, if I look at a system at equilibrium, what are its characteristics? That's what these 6 are, okay? The 5 conditions necessary for equilibrium is, you say, what do I need in order to be able to have an equilibrium? Okay? It's a bit of a subtle distinction. What I would like you to do is I would like you to read through these 6 and decide if any of them are also conditions necessary for equilibrium.
I'm willing to be wrong. I think I went to read. Okay, so I'm reading before. Okay, and then 4 and 5. So 1, 4, and 5. It's fun. Well, how the average?
It's okay if you're wrong. Okay. Which ones are definitely also conditions necessary for equilibrium? Number 3 for sure. Okay, so I'm going to highlight them. System has to be closed. What else is absolutely necessary for equilibrium? 4, the temperature must be constant and uniform. And we also need 6, both reactants and products must be present. All right, and let's see, what are the other ones? That's 1, 2, 3. The first one, yes, the forward rate and the reverse rate have to be equal. And I know this one seems redundant because we've already said there's a forward and reverse rate, but the 5th one, so this would be like number 1, 2, 3, 4. The 5th one, which would be conditions necessary for an equilibrium, would be that it must be a reversible reaction. Now, how fussy am I going to get? If I ask you, please give me 3 characteristics of a system at dynamic equilibrium, you could say that the reaction is reversible, but you wouldn't say the reaction must be a reversible reaction because that wouldn't be a characteristic anymore. That is a condition necessary if you phrase it that way. Do you know what I mean? So what you have to look at is you have to look at your language and how you use it. If I'm asking you, what are the conditions necessary? We need to have a reversible reaction. We need to have a closed system. We need to have a constant temperature. We need to have both reactants and products present. Yes? But if I say, what are the 5 characteristics? Oh, forward rate equals reverse rate. The macroscopic properties are not changing. I have a closed system. I have a tense. So you notice the difference. One is I need to have blah, blah, blah. The other one is I do have blah, blah, blah. Okay? And the one that, the couple that can't really be, I don't know. This one where it can be approached from either the left or the right, that one always, I don't know. It makes me a little unhappy because it seems sort of stupid, but, you know, just go with it. Okay? I won't ever be asking you for all 6, so you can pick the 4 or the 3 that make the most sense to you. Does that make sense? Okay. All right. There's some exercises. These are going to be your homework for the day, so it's going to be pages 20 all the way through 23. Okay, that will be your homework. And for homework, pages 20 to 23. But we're not going to do that today. We are going to go through stresses and shifts. I would like you to see if you can fill in the blanks in that very first little paragraph. This is on page 24. See if you can fill those in. Okay, don't worry about the rest of that. Color is an example of macroscopic property. In other words, an observable property. At equilibrium, what kind of properties? Macroscopic. Properties are constant. And what is true at equilibrium? What is equal at equilibrium? Forward rate is equal to the reverse rate. All right. Now, a system at equilibrium will remain at equilibrium until it is stressed. And a stress, remember, is a change that we make to an equilibrium, and that's a change that makes the rates unequal. Now, we're going to learn about how long we're going to look in the context of graphing. A stress is considered to be instantaneous. In other words, it takes no time. In reality, that's not true, but it makes graphing possible and readable. So we assume that anything that we do to the system takes no time at all. And if something takes no time at all on a graph, what does that look like? If something is increasing in no time at all, it just goes up, straight up, vertical. Okay, because if it goes up on an angle, that means it's taking some time. It's going up as time progresses. But if it takes no time, it's vertical. Okay? So because it takes no time, it's going to appear as a vertical spike. And today we're going to be starting to learn about concentration and rate graphs. So here we're just going to take a look at what that looks like if we have a stress. Don't worry about what happens after the stress. We will get to that. Concentration. Concentration versus time. That is a concentration graph. Now let's assume that we are talking about and actually let me just check and make sure I'm doing this the right way so I'm consistent between the two classes. Oh, here we go. N2O4 in equilibrium with 2NO2. So there's our system, which is at equilibrium. And for my concentration of NO2, I'm going to put it there. Why did I choose that? No reason at all. The amount is arbitrary. Okay, there was no good reason for me putting it there. I could have put it anywhere else instead. And I'm going to put my concentration of N2O4 here. And taking a look at what's happening to those concentrations as time is moving on, what can you say is true during this part of the graph? They're constant. The concentrations are constant. What does that tell us about the system? We are at equilibrium. Because what is concentration? Concentration is a Macroscopic property. And if macroscopic properties are constant, we are at equilibrium. Okay. Now, what's going to happen is right here at this time, I'm going to inject some N2O4. And in case you're like, what do you mean you're going to inject some N2O4? What I would mean, I emptied these out since yesterday because the gas eats away at the rubber stoppers. So if we want to keep our rubber stoppers in good condition, we don't let them sit there in that exposed to that gas for too long, okay? But we're going to pretend the gas is in here, yes? So we have some brown gas in here. We have some colorless gas in here. Now let's say that I have a syringe. Do you guys know what a syringe is? It's like a hypodermic needle, yes? I have a syringe full of N2O4, okay? And I take that syringe and I jab it right through the rubber stopper. I guess it's got to be a pretty heavy gauge needle, right, to go through. But anyway, I jam it through and I go squish and I push all the N2O4 gas into here. So what has happened to our concentration of N2O4? It has increased. So we inject some N2O4. So the concentration of N2O4 increases. And this is something, is the system putting in N2O4 or are we putting in N2O4? We are doing it. So what is that? That is a stress. And how much time does a stress take? It is instantaneous. It takes no time. So how would I draw that on here? I would draw a vertical line for who? The N2O4. Okay? So that right there is our stress. And if it takes no time, therefore it is vertical. So that's what a concentration graph is going to look like, at least up to the stress point. Tomorrow, we will be looking at what happens after the stress. We won't get any further than that today, though. Now, the other kind of diagram we can draw is a rate diagram. So guess what the only thing we change is? We change the y-axis to rate instead of concentration, but the x-axis still remains time. And we're going to be looking at this same reaction, the N2O4 in equilibrium with 2NO2. And we are starting out, remember when we started out, these concentrations were constant. And so we were at equilibrium at the start. So if I'm going to have the blue line represent my forward rate and the reverse, the dashed line or the red line represent the reverse rate, what will they have to be like initially? Will they be the same or will they be different? At the beginning, we are at equilibrium, so the two rates will be the same until we inject some N2O4, okay? So we will have our forward rate equal to our reverse rate, because here we are at equilibrium. And then once again, we are going to, oh, I shouldn't have drawn that there. Bad, Ms. Spence. I should have drawn it higher up. That's okay. At equilibrium. Okay. Now, here, we inject N2O4. I would like you to tell your partner what happens to the forward rate and what happens to the reverse rate. Okay, so in that instant, the concentration of N2O4 increases. So what happens to the forward rate? The forward rate increases. So what that's going to look like, remember, this is a stress. And anything that is, any change that is due to the stress takes how much time? No time. So the forward rate is going to increase. And a stress is instantaneous. Okay, therefore it is vertical. So that's our forward rate. What happens to the concentration of NO2 in that instant? So I've injected some N2O4. In that same instant, what happens to the concentration of NO2? I'm going to let you finish writing. There's people still writing, so I'm going to let you finish writing, then we're going to go over this. I put in extra N2O4. That made the N2O4 concentration go up. What did I do to the concentration of NO2? I did nothing to it. So what happens to the concentration of NO2? It just stays the same. It will change later, but right in that instant, there is no change, okay? Because we're just dealing with the instant of the stress, okay? In that instant, it stays the same. Later on, we will have a shift. Concentrations will increase, concentrations will decrease, but right in the moment of the stress, there is no change to NO2. Now, what things can be stresses? Remember, it needs to be something we can change, and it needs to change the rate and make the rates unequal. So if I change the concentration, I will be changing the rate of one direction or the other direction. Yes? So a change in concentration is a stress. Why pen no work? I don't understand. Let's try that again. Concentration is a stress, a change in concentration. If I squish the container, I am changing the concentration of the gases, yes? So a change in volume pressure will also change the rates. And of course, changing a temperature changes the rates. Now, there are things that are not stresses, and you might be like, but adding a catalyst would change the rate. But here's the deal. A catalyst speeds up the forward and reverse rates by the same amount, so the rates stay equal. So you stay at equilibrium, okay? So a catalyst speeds up both forward and reverse rates equally. So a catalyst speeds up both forward and reverse rates equally. Therefore, the forward rate still equals reverse rate. Therefore, we are still at equilibrium. And that's why it's not a stress. If you're still at equilibrium, the system is not stressed. Now, surface area, we're going to use a little example here where we have a flask, just like the one we had yesterday. Okay. And we're going to use a really simple system here. Okay. I'm just going to do evaporating a liquid. Yes. So we have a liquid here. And some of that liquid evaporates out and gives us some gas particles. Yes? Now, every time, if this is a closed system, every time one particle evaporates, what has to happen to a different particle? A different particle is going to condense. Okay? Now we're going to make the surface larger. And we're going to do that by making a really weird shaped flask. Okay? Bizarre shaped flask. That looks about the same concentration, doesn't it? Okay, approximately. Now, where does evaporation take place? It takes place at the surface. Where does condensation take place? It takes place at the surface. So what's going to happen is I have now provided 3 times the area for evaporation to occur, so the rate of evaporation is going to triple. Yes? And I have also provided 3 times the area for the condensation process. So the condensation rate is also going to triple. So if we triple the surface area, we triple the forward rate. But we also triple the reverse rate. So yes, surface area changes rates, but it changes the rates equally, just like a catalyst does. So if you've got them both fast and now they're both slow, but they've slowed down by the same amount, you still have equal rates, so you are still at equilibrium. Okay? So surface area also speeds up both forward and reverse rates equally, so we are still at equilibrium. And the final one we have is an inert gas. Do you guys remember what inert means? Inert means non-reactive, yes. Okay, and because it is non-reactive, will it have any effect on rate at all? No effect on rate. If you remember that from our reaction rates unit, it just has no effect on rate. And people keep asking me, why do I bother mentioning it? Because sometimes people think, oh, the question will say, we have increased the pressure. Oh, and they hear the word pressure. Pressure has changed by adding an inert gas. What happens to the system, right? And the answer is nothing. Nothing happens to the rate, nothing happens to the system. And I think you guys need to go out and walk around for 5 minutes and be back at 1:45, and then we are going to finish these notes, okay? Be back at 1:45. Walk around, get some water.
Oh, you can walk around and do water.
So in this case, if you change the concentration of the reactants and products proportionally with
It will still be at equilibrium, but when we're talking about a concentration, usually we're only talking about changing one thing. Yeah. But yes, you're absolutely right. And that would be like if you had 1 mole of gas in the reactants and 1 mole of gas in the product, and squish it, that will change the concentration. Like, our friend who like maybe having like that, but and then like it was like yeah, like too much. Wouldn't be like she said he screenshot and stuff. Oh, there it is. And sources started contradicting each other. After we saw it, they got me. There we go. Okay. So what I would like you guys to do now is I would like you to list the 3 things which are stresses and the 3 things which are not stresses. We just did it a minute ago. You should be able to do it now. So it's on the next page. Nope, right here. At the top of the page it says 1, 2, 3, 1, 2, 3. If you have trouble thinking of them, 5 of those 6 things are factors that affect rates. Right? Because we're looking at things that affect the rates. What are the 5 factors that affect rates? Number 1, concentration. Number 2, volume pressure. Number 3, temperature. Number 4, surface area. Number 5, catalyst. Okay, and of those, the 3 that are stresses are 1, 2, 3. So we have concentration, volume pressure, and temperature. The things that are not stresses are surface area, a catalyst, and now we just need to think of something else, and that would be a inert gas. Yes. Now, concentration, volume pressure, and temperature temporarily make the forward and reverse rates unequal. And they can do this either by changing only one of the 2 rates, or they can do it by changing both rates, but by different amounts. So what I would like you to think about is, out of these 3 factors here, which of these 3 factors changes only one of the 2 rates? Concentration, volume/pressure, or temperature? And when we talk about concentration, we're talking about the concentration of one species. Otherwise, it's too complicated. So which one changes only one of the 2 rates? Concentration. Now, volume pressure, we're going to assume, we have a gaseous system. Just to make our lives simpler for now, okay? We'll look at systems where it's both things later, but we'll assume everything's a gas. So if we change the volume pressure and everything is gaseous, will we be changing only one of the 2 rates, or will we be changing both of them? We'll be changing both. So volume pressure changes both rates. And how about temperature? Does temperature change only one of the 2 rates, or does temperature change both rates? Both. Now, if we have 3 things, or 3 things which are not stresses, we have surface area, catalyst, and an inert gas. These 3 things leave the forward and the reverse rates equal. They can do that either by increasing both rates equally. out of those three factors, which things change both rates equally? Catalyst. How about surface area? Does surface area change both rates equally? Yes, it does. So surface area. Okay. Now, the other way that you can have a system still at equilibrium is by not changing either rate at all. Yes, if they all just stay the same. And who changes neither rate? The inert gas. And this is as far as I got with the other block. Oh, look at that. We're done early. Yes, for once. We're not having to be like, oh, please watch video 7. Oh my God, I feel so bad for doing that to you guys. But I can't have you in different places. It's just too weird. You're done early. Your homework is pages 20 to 23. You are welcome to work on that. You are also welcome if you need to use the bathroom right now. But remember, there are rules around using the bathroom, right? You don't go anywhere near the office. Yes, if you use the bathroom. Yes. Okay.
How? I know I'm really funny.